Greetings, geologists, and we are here to learn about the Quaternary period, which is the very last period of the geologic time scale, so that should make you happy. An interesting period indeed. This includes the last 2.6 million years of time, of which most was dedicated to the last ice age. Only the last 10,000 years was dedicated to the Holocene, which is the modern epoch of time. So out of every period on the geologic time scale, this is by far the shortest one. So there are two epochs that you need to be familiar with for this time period. In the Quaternary, from oldest to youngest, the Pleistocene is referred to as the last ice age, but its name means most new. That can be confusing when you look at Holocene, which means most recent. So make sure you're clear on which one's most new and most recent. Most recent means it's happening at the current time. Most new is it's the newest epoch that's been completed. So during each segment of time, there are very specific animals that lived and unique climate conditions that occurred that separates one from the other. When you think about Quaternary age sediments, matter of fact, any Cenozoic age sediments, you should be thinking yellows and orange. And in our case right now, we're really heavily emphasized onto the dark oranges that exist where the last ice age put down terminal moraines, as well as on the yellowy parts where you see ice age valley glaciers that might have come down in the mountains in this area right here. So we can kind of look at the areas that contain mountains and then the areas that would have been heavily impacted by continental glaciers and the toes of valley glaciers that might have come off of them. You can even see some of that down in this area as well. So very interesting thing to contemplate is where do we find the deposits? Let's give you a clearer view on that. First of all, let's talk about what was going on during the Quaternary period. If you recall from the Tertiary, ever since the PETM, we've had a pretty much gradual cooling trend in climate. By the end of the Pliocene, we have no doubt full ice sheets that can be in both hemispheres, meaning at the northern and southern poles. In other words, the ice sheets have stayed year-round in the Arctic Circle and the Antarctic Circle. That's important because the Arctic Circle really hasn't been bearing ice sheets until that time when continents have moved in such a way to kind of landlock out the northern hemisphere's Arctic Circle from getting good circulation of ocean currents. So by now in the Quaternary, our continents have reached the current positions and the cooling trend is going to really reach a point where ice begins to migrate downwards from their roots or their heads. And we're talking about continental ice packs right now. And there are three definitive packs that exist in North America, of which one has a broad name that's divided into two separate pieces, and we'll look at that. So the plates that have moved to their current locations ended up kind of landlocking in this area right here, allowing for ice sheets to grow in the northern hemisphere, which has not been seen since snowball Earth. So this is very important change in dynamic that's going to set the stage up for a sequence of ice ages in the northern hemisphere that has not been experienced through all of the Phanerozoic. Because heat was not evenly distributed at the Arctic Circle, the Arctic Ocean froze over, allowing for a major climate shift and ice to really form in our northern continents. Notice that Greenland's moved this far north, and then we're getting ice sheets that are migrating downwards into the continents. The same thing happened in Europe. And to be truthful, more episodic events happened in Europe, but we just have better terminal moraines. And so our terminal moraines are very famous for this time period from a very specific ice sheet that we're going to be learning about. This diagram only shows you a little bit about glacial deposits. Doesn't even show you what's happening in Canada, because Canada would be a big old solid yellow. Here's what I want you to take away. Let's look at the yellow first. These are glacial deposits, in particular terminal moraines. And then the green and the pink are specific types, and this kind of dark reddish color are specific types of moraines that were deposited during the last ice age that are named after the furthest state that this ice pack traveled into. What I want to point out is the heavy yellow represents the toes of the continental glaciers that came out of Canada and Alaska. These right in here are going to be dominated by the ones called the Laurentide, and this stuff over here is going to come out of the Cordilleran, which originates in Alaska. So you might wonder what these random yellow things are over here. Those are going to be valley glaciers from mountainous areas of the Rocky Mountain Range, the Sap Cascades, things of that nature. Now let's look at the gray. Check that out down here. That's pluvial lakes. Remember me talking about the difference between fluvial river versus pluvial, and I told you that they couldn't be the same? Well, today's the day you learn why. Pluvial lakes are special features that were created in the last ice age, and that's some very important water resources out west. So the Quaternary ice sheets removed water two ways. They lowered water in the ocean by sea ice, but you have to imagine that the ice that formed on the continents wasn't pulling water from the ocean except through the hydrologic cycle that would have fueled if you had wet conditions and cool enough temperatures to create glaciers. So the sea ice definitely plays a role in lowering sea level, but this part right here is different. It comes from circumstantial, all the things aligned in the right order in order for us to make firn, which is the snow that compacts and recrystallizes into glacial ice. So all the right factors had to be in place for these areas to work. That means that as sea level dropped by 300 to 400 feet in some areas, test question, 300 to 400 feet is the drop of ice or sea level because of the ice. You have to imagine that areas that are submerged today were fully exposed. So that means at that time, animals could have actually had their fossils be found in areas that are currently covered by the ocean. And we may discover some if we do subsurface drilling or excavation along the edges of our continent. Now there are two primary major ice sheets. There's one that comes out of out of Alaskan area right here, and it has a big C on it that stands for Cordilleran. That's no surprise since this is the Cordilleran Range. So I'd like you to notice that the two marry up right about here. Now, this big large thing right here is referred to as the Laurentide. That's its general name, Laurentide. Having said that, in this class, it's important enough that you understand that the Laurentide is divided into two primary pieces because they have two origin locations, in other words, two heads of the continental glacier. One exists up here and one exists over here. The L stands for the Labrador, and this one right here that begins with K, Quaternary. Quaternary is actually a series of lava flows that were famous from the Precambrian. If you recall back to Precambrian, those lava flows out of Canada that were proof of Rodinia, that actually was the first supercontinent of geologic time that we have a record of. So what's going to happen is if these grow, they're going to grow down and come back up when they retreat. So they're not going to be a solid white for the duration of the entire ice age. That's a misconception that the ice age was one giant ice box. Instead, they're going to have gradual growth. That means the Quaternary and the Labrador can grow at different speeds. Subsequently, the amount of time lap over between these two of when they bring in the ice packs into North America have some shared time. You also need to imagine that while the Cordilleran's growing, it's so much smaller. It's not even a quarter the size of the entire Laurentide right here. It's just a runt. It's just tiny. So at times there probably was a pathway for animals to travel between this without having to walk over extensive continental glacier land. If not, and animals and humans even migrated over this, you have to imagine that was pretty rough migration situations. Very important to point out, this area down in here, especially where you see the orange, these are very specific terminal moraines and outwash plain deposits that we have a very extensive set of blankets for, that also provide very fertile ground for the Midwest to grow crops. My point is this: if this stuff is right here, which is our sheer plain evidence that we know that the last ice age occurred, and we can tell definitively how far the ice migrated into North America. Each ice sheet had a different duration of time. So let's look at each one, and for test-related purposes, do you know where they originated? Meaning like the Laurentides in Canada, and it's broken into two pieces. And do you know how long that it melted? So in the case of the Laurentide, this was the massive ice sheet that originated over parts of Canada and covered hundreds of thousands of square miles of the Canadian provinces. It even made its way into North America, and we can dictate how far it came by the 4 terminal moraines we find in the United States, which we'll get to in just a minute. This ice sheet was so large that it took approximately 11,000 years. Guaranteed test question: the Laurentide came out of Canada, and that it took 11,000 years to melt. This would be gradual climate changes, but also lead to some significant stream development in this area. I'm going to kind of jump ahead and say that could be very important for loss of life, like mammoth herds that might be nearby that get into mudslide type situations as these ice sheets are gradually melting, and you have interesting circumstances by which that would have flooded out the terrain and their food resources. The second Quaternary set of ice sheets comes out of the Cordilleran Alaskan area. British Columbia, Alaska, Montana, Idaho, these were all areas that were impacted by the Cordilleran ice sheet. So for example, Glacier National Park, that you've seen a lot of in videos this semester, that would have been impacted by the Cordilleran ice pack. This was a very fast melting ice pack, which is important, especially along this area, and I'm going to kind of give you this shape because I'll revisit that in a little while. That is going to be rapid melting, created kind of like flash flooding conditions. This only took 4,000 years to melt, and when it did, it created some very interesting runoff conditions and left behind some unique landscapes as a consequence of river erosion. During the Pleistocene, we would also have a climate out west that would create a number of pluvial lakes. These lakes are referred to in a special manner because some of them actually still exist today and make the bottom sections of the basin and range that have filled up with water and become some of the most important surface and groundwater supplies that we have out west. All right, getting back to glaciers and how they migrated in and out of North America. You need to know this for the test. They migrated in and out 4 times. So what I'm telling you is we had an ice advance, it got warm and they retreated. Second ice advance, second retreat. Third ice advance, third retreat. Fourth ice advance, fourth retreat. We are in the 4th retreat right now, but evidence would suggest geologically, biologically, and ecologically that we will have a continuation of the last ice age in spite of a climate warming trend. So another trend that we see by taking ice cores from Greenland is that the ice cycles last much longer than the interglacial periods. The interglacial periods are the warming sections like we have right now. So you have to imagine at the peak of the last ice age in the Pleistocene that as much as 30% of North America was covered. But the glaciers never made it this far. The farthest travel extent was to the far northern section of Kansas. So they didn't even make it to Oklahoma. So I'm not telling you we didn't get runoff in the forms of river drainage that could have occurred, but I'm telling you, you're never going to find a glacial erratic out here. You're never going to find moraine deposits in Texas. You're just not going to find that. You have to imagine that these ice packs, these continental ice packs, get up to 13,000 feet. Well, folks, that's more than 2 miles thick. So if you'd like to contemplate what that looked like in New York, in this area of the United States at the peak of the Wisconsin ice sheet, which covered that area, you have to imagine that all the skyscrapers in New York were completely under ice. That's just mind-boggling. So let's take a look at some of the evidence that we have for the last ice age. We know that large continental glaciers covered the continents, but how do we really know? They left behind their deposits and some clues. But the continental glaciers were not the only areas that gave us proof. For example, we know for sure that valley glaciers did the same thing, coming out of the mountains. Interestingly enough, we even see valley glaciers that grow during the last ice age in Hawaii. Go figure. So all over the world, valley glaciers were moving and growing at the same time continental glaciers were, and they left behind us so many incredible clues. So let's keep looking. Notice that the ice sheet came down, and where it did, it left behind these thick orange blankets of sediment. So we're going to be focusing on those. Those are called terminal moraines. That's the furthest travel extent of a glacier. Each advance of the Canadian ice sheet, known as the Laurentide, get named after their deposits of terminal moraines that they left at their furthest southerly travel extent. So you're going to need to know for test purposes the length of time, like how long they lasted, in the case of the Nebraskan, 800,000 years to 300,000 years, and understand that you had ice coming out of the Quaternary and the Labrador ice sheets at the same time. So there can be some crossover in time. So the oldest of the ice sheets that happened during the last ice sheet that made it all the way into North America was the Nebraskan ice sheet. And the Nebraskan ice sheet came to about right here. That's the furthest extent. So that took 800,000 to 300,000 years, and then it would start to work its way back up. At the same time, the Labrador is going to work its way down all the way to the northern tip right here of Kansas. And that's going to be the Kansan ice sheet that took us about 600,000 years to 200,000 years ago. The Illinoisan ice sheet was going to originate in the same area right over here, and it's going to last from about 250,000 years to 135,000 years. One of the most noticeable and famous of the last ice age ice sheets was the Wisconsin ice sheet that came all the way down from the Labrador and worked its way in through New York. So if you went to New York Central Park, you would see a lot of evidence that the Wisconsin ice sheet had existed there 100,000 years ago to the conclusion of the last ice age, which was about 10,000 years ago. So let's look at evidence, proof, in the rock record and some interesting other places too, that we know the last ice age appeared. I love this. This may be my favorite piece of proof, but glacial erratics are rocks that just don't match the neighborhood. They're out there. Where the heck did they come from? These are rocks that got picked up by glaciers, carried down until they got deposited when the glacier could no longer melt. Some are small. Many of them are car size and bigger. And so we see this with both valley and continental glaciers, but the key is they just don't match the neighborhood. In some cases, rocks like this one at the top of Cadillac Mountain they don't match the rock from the mountain. So where the heck did they come from? They're just sitting out in the middle of nowhere. A good place to see this is in Grand Teton National Park. And so Grand Teton has a series of clues for the last ice age, and it's really fascinating. In 1937, a guy by the name of Louis Agassiz came up with this concept about glacial erratics, and people thought, oh, you were crazy. What are you thinking that these things were in icebergs? And that's what they called them, ice sheets or icebergs coming down into the continent. Well, he said, no, they were in big ice packs known as continental glaciers. And I am certain that these got picked up and transported and weren't transported by a river because they don't have river or fluvial depositional evidence. He turned out to be right and ended up getting a lake named after him in Canada. Here's another glacial erratic in Colorado. It doesn't match. It got plucked off at the top of the mountain, brought down in the last ice age, and left behind for us to see today. Other evidence for the last ice age, especially for continental glaciers. Significant polishing and scratching in the form of glacial striations and even glacial grooves. Glacial grooves are deeper than glacial striations, but nevertheless, you'll see both and even on the same rock. Like you can see these lines right here. Here are lines in the rock. And then see how smooth this is? That comes from glacial polishing where you get silts, glacial silts where it comes in contact with bedrock. It makes a thin layer almost like sandpaper that will smooth out the landscape as those big glaciers come through the neighborhood. All glaciers can create scratching and polishing, both valley and continental, but continental did such a huge, massive area and left behind evidence. We can even follow, really interesting, we can actually follow the direction of the scratches and tell you the direction of the flow of the ice packs. Glacial till is another piece of evidence for glaciers in the last ice age. This is sediment that's directly deposited from glacial ice and is not well sorted or stratified, in other words, like a graded bed. This type of sediment is found really interestingly all throughout the Midwest at the edges of the ice sheets where the melting occurred, and it's very useful for economic and agricultural use. Another big piece of proof for the last ice age are gigantic U-shaped valleys from valley glaciers. Now, continental glaciers don't make U-shaped valleys. This is in one of my favorite places on the planet, which is Glacier National Park. And can you see this big U profile right here? What I'd like to point out is the ice probably came all the way up to here. How do we know that? Because the steep walls were carved out by the ice. And then when they melted, they left behind this U profile. If it was a river, it would look like this. While there is a river down here today, and this is going along the Sun Road right here is what it's called in the park, this can't be made by any other thing in the world except valley glaciers. And they're all over the place from the mountainous regions that had valley glaciers growing in the last ice age. All right, one of the weirdest pieces of evidence for the Pleistocene is marine isotopes. What are those? First of all, we look for the ratio of oxygen 18 to oxygen 16 by mass in deep sea deposits. And what we do is we take a mass spec and we look at them and we try to determine the calcite origin. In other words, how did the calcite get made in ocean core samples? It is simply a diagnostic test to look at ancient ocean temperatures because certain amounts of oxygen isotopes exist in cool conditions versus warm conditions. So what are we looking for? If I see a sediment core that's rich in O18 or even better yet, an ice core, if we can get one of those from somewhere like Greenland, it should be high in O18. During the warmer areas, you can see the sediments will contain a higher concentration of O16. So that's all based on the amount of calcite made by microorganisms like foraminifera. So we can actually distinguish the fluxes of cold simply based on looking at marine isotopes. Pretty strange, isn't it? Probably even stranger than that is looking at marine foraminifera and how they coil when they develop in oceans that are cold. Certain species of forams love cold conditions and still do today, but they will coil in the opposite direction from other types of warm climate type forams, and we just see their fossils in these ice sheets in the sediments and in ice cores today. very interesting trigger proof for us to go look at microorganisms to prove the last ice age really occurred. We can even tell you by the thickness of the ice sheets or how thick they were by looking at the current cores today and the depth at which they press down the continents. So these are the two cores, the Quaternary here and the Labrador here, and they grew respectively in these directions until they came into North America. Now the Cordilleran originated right about here and came down this direction right there. So with that in mind, these areas are still have some ice, and they've been depressed down because this would be the thickest ice packs would have existed in these areas right here as they grew out laterally and down south into North America. Which brings me into a concept of glacial isostasy. This is where the land or the lithosphere gets pushed down, depressed beneath the weight of the ice, and subsequently rebounds when the ice melts. So I'll use the example of the woman in the dentist office that I used earlier in the semester that sat on the couch when I was a kid, and I noticed that when she got up there was an indentation in the couch. Well, and 30 minutes later that indentation was back to normal, and that just blew my mind. As a 7 or 8-year-old, how could that be, right? So this is on a larger scale. You have to imagine these continental glaciers grew thousands of square miles. And so if they got between 2 and 3 miles thick and they cover this gigantic regional area, you're going to have some serious weight, just like mountains would produce on top of land. Since mountains take a lot longer to erode than glaciers do to melt, this means that the fast melting would allow for the land to pop back into place. Some of that rebounding has been fairly substantial. Here is an exact area that happened. You can focus on parts of Hudson Bay way up here in Canada, and these areas have beach-line deposits that were at the shoreline in the last ice age. We can date their sediments. They have rebounded 1,000 feet since 14,000 years ago. Wow. 1,000 feet of elevation change. That's as different as the south rim of the Grand Canyon is to the north rim. That's phenomenal. That means that you're getting a foot every 100 years, essentially. You know, you're getting quite a bit of rebound that's happening, and that is substantial. If you had housing structures that were built on that type of rebounding structure, that could totally redecorate an entire city if it moves at 1,000 feet. Another piece of evidence, remember our glacial erratic guy, Mr. Agassiz? Well, poor guy, his lake got named after him, and there were some problems with his lake. Glacial dams were created where massive rock and moraine deposits got deposited along the edges of glaciers, as well as what we call recessional moraines, which is when they start heading back up to their origin source. And Lake Agassiz was actually blocked in by glacial dams, and part of that catastrophically failed and flooded. A couple of these lakes did that and flooded out areas down in this part of the continent. Interesting thing else to point out here, that the superior lakes as you know them, or should I say the Great Lakes, not just Lake Superior, but all of the Great Lakes, were created back in the last ice age. I think that's important for you to know. A really important piece of evidence is something called the scablands. This occurred at the toes of the Cordilleran belt, and I want you to check out the edge of this thing, almost look at its shape. And it created this weird landscape right here because the Cordilleran belt was scoured away because of fairly quick, remember 4,000 years of melting for the Cordilleran ice sheet, and left behind some really interesting scarred up land. Here's what that land looks like. So you have to imagine the toes of the glacier were coming this way, and this is why it's so deep, and this is pretty ravined area, and then they melt and catastrophically create glacial dams, and when those dams fail, flooding downstream occurs. So it makes a spectacular canyon display of channels, river channels from melting glaciers that break the flat layers of basalt that were laid down during the Tertiary, if you recall learning about the massive flood basalts out there. And what happens is these get eroded by glacial lakes that drained out at the end of the last ice age from melting glaciers, and these would be where those glacier lakes used to be. The shorelines of pluvial lakes also are clues that the last ice age occurred. And what happens is we got enhanced rainfall during the last ice age. You have to imagine that the climate was wet and cooler. Most of these lakes have dried up today, leaving behind dry basins. Some of them still contain water, and some of the water exists subsurface as groundwater. But pluvial lakes are really important evidence of water resources that would have been rich and plentiful back in the last ice age. Let me point out, that's important to where we find a lot of ice age animals in the fossil record. Keep that thought in mind. All right, let's talk about how glaciers formed in the last ice age and why they formed. There was a gentleman by the name of Milankovitch, which is a Serbian mathematician, who came up with a theory about how these particular ice ages could have happened so quickly back to back, considering that all of the ice ages cumulative throughout geologic time pretty much match what we have all over the course of 2.6 million years. So how is it possible that they were so well spread out by hundreds of millions of years throughout geologic time, then bam, 1, 2, 3, 4, smack dab in the middle of North America? So he came up with some mathematical equations that help explain this. There were 3 parts to his theory. The eccentricity cycle, and that deals with our orbit around the sun. I'm going to make this thing right here the sun, okay? And so actually, yeah, this would be the sun, and we're going to move around the sun. We move more like this direction right here, but in an elliptical year, we would move more like a very flat egg, like you see right in this section right here. So what ends up happening is when we make this longer stretch around a year, we have longer and cooler winters, springs, summers, and of course colder winters. And you're in this cycle and you have definitive 4 seasons, but you have a much hotter summer. So this alone, if you have the extent over 100,000 years, that cycle gradually reaches probably the last 75 to 100,000 years, you're going to end up with substantial potential for ice growth during parts of the times of years you wouldn't normally have it. The obliquity cycle is based on, if this is Earth, how we're tilted and where our imaginary axis is. So we do have an axis that we spin on. Just a couple of degrees and a half difference can change how much direct solar radiation we get at the top of our Arctic area. And so when that's at its more straight up, we end up with having less direct solar radiation at this point in the Arctic area, which is going to produce ice ages or help produce the right conditions to do so. The precession of equinoxes, I'm not going to test you on these years because this one's a more difficult concept. It basically boils down to, is our axis pointing towards away from the sun or towards the sun? If we're pointed away from the sun and we're tilted at this obliquity cycle here, I'm going to have less direct solar radiation, which can actually be pretty substantial. The eccentricity cycle takes about 100,000 years to get from our normal cycle around the sun to our fully elliptical. The obliquity cycle takes about 41,000 years. So you can see how there could be some crossover more than once between the eccentricity and obliquity. And certainly when you're looking at the precession of equinoxes, as short a period as 19,000 and 23,000 years, you can see that those could happen 1, 2, 3, and 4 times over the course of 100,000 years. So what we know is that most of the ice cycles took a good 100 or 200,000 years to occur, and then the interglacial periods were very short, somewhere between 10,000 to 20,000 years long. So that shouldn't make us feel too good considering the last 10,000 years were an interglacial period. This would be a really great place to take a break. So we're going to take a break at this moment, and then we'll come back and we'll learn about humans and animals. So take a minute to go stretch your legs, and we'll come back and watch part 2 shortly.